Hi, everyone. Welcome to our talk, Feature Drift Monitoring as a Service for Machine Learning Models at Scale. My name is Keira Zhou. I am a data engineer at Capital One.
Hi, everyone. My name is Tatsumi. I work with Keira, and I'm a director of engineering in Capital One's Card Technology division. Before we dive into the details of the system, I'd like for us to get aligned on a couple of terminologies. The first is feature. It's an overloaded term in software engineering, but in machine learning, it's a descriptive attribute that's used as an input to a machine learning model to make some sort of prediction. A feature drift is a change or a shift in the joint distribution of a feature and a target. What you see on this slide are different types of feature drifts. It can be a distribution change in values or sometimes the associated labels. Alternatively, drift might be referred to the relationship between the feature values and the labels. So because machine learning is learning from data or the features, it's really important that the features are monitored, especially for business critical machine learning models. As a company, you don't want to take a risk on not monitoring your features because many models are brittle, and the impact may be that you incur a significant financial loss or harm to the brand of your business. This is why we built our feature monitoring solution that's accessible to any of our data scientists and engineers in Capital One. Our service platform helps detect feature drifts through statistics and model-based metrics. The metrics include descriptive statistics like mean and standard deviation. We have some data quality metrics like record count and number of nulls to make sure that the upstream data pipeline is healthy. For our analysis service, we have Population Stability Index, or we just call it PSI. PSI is a measure of how much a feature has shifted over time or between two different samples. We also offer a model-based analysis for time series change point and anomaly detection to indicate abrupt and significant changes. So our platform provides our users the access to all these metrics and analysis through various interactive interfaces like visualization dashboards, API, SQL interface, and alerts. With the capabilities that our platform offers, our users can continuously make sure that their models are performing well. They can use the interactive interfaces to derive signals to retain a model, proactively make decisions on whether they want to use a feature or not, or explain why their model has shifted. So to offer the services or a service to multiple teams and models, we need to make sure that our platform is able to handle the scalability from both functional and non-functional requirements perspective. To achieve that, we made these 5 key design decisions while building the platform. The first is that the features are pre-registered in a feature catalog so that we can identify them and determine how to access them. We're also making sure that the features are sorted in standardized format so that we can read them easily. The second design decision was to have our clients or client users and applications get their own access to the features they want to monitor and provide that to the platform so that the platform doesn't have to have access to massive volume of features in Capital One. This was definitely a challenging problem to solve, but it was our top priority as a bank. The third decision is to enable our users to specify their own aggregation keys. without this capability to tailor our outputs to the context that the model developers are working with, the metrics and analysis that we produce will likely be completely useless. Our fourth decision was to make sure that we build a system in a way that our users aren't stepping on each other's toes by incorporating distributed processing techniques and robust orchestration layer. And lastly, because qualifying a feature drift is very specific to each model, we provide tools to visualize, slice, and dice the metrics and analysis that our platform produces to empower users to make their own conclusion decisions on when and what to do with their models. So next, Keira and I are going to double click on the implementation details of these design decisions. So the first thing we'll cover is the data pipeline architecture. This is essentially what makes various features discoverable and readable to the feature monitoring platform. So to my team's luck, Capital One has a reliable and robust enterprise common capability for data cataloging, data ingestion, and persistent storage that almost all applications use already. So with these services, the feature compute functions can calculate features in just-in-time, streaming, or batch fashion, and send the computed output to the ingestion service for the data to be persisted in Parquet files with file location, partition keys, and schema available in the data catalog service. The ingestion service can take Avro messages from streaming and just-in-time API services or whole files from batch systems.
Thanks, Nori. So now I am going to talk about the technical details of our feature monitoring as a service. This is our architecture diagram. So we have a trigger API as an enter point to our monitoring service. So the trigger API connects to the Airflow and it spins up EMR cluster that runs a PySpark job. You may notice that we also have a Redis cluster. The need for that is to cache our API requests so that we don't accidentally receive like 5, 10 same requests and spins up too many EMR cluster. The stats computation are done by Spark running on EMR, and the output is sent to our enterprise Kafka cluster. Our enterprise Kafka has the capability of save the results into our enterprise AWS S3. And also we have our own ingestion engine that listens to our stats topic and writes the output to Postgres. As a serving layer, we provide a Grafana dashboard as well as a GraphQL API. The other thing I want to point out is we have external team that builds machine learning as a service. We partner with them so they can use the stats we produced and run more advanced analysis and algorithm on top of that to do feature drift detection. Next slide. So the first thing I'm going to talk about is our trigger API. So it triggers and configures our feature statistics calculation. As Nori mentioned that we have an enterprise feature registry, it provides every feature a unique ID. So we receive a dataset location ID from our client and use that to query our feature registry API and receive a list of feature ID. And that information is used for us to uniquely identify a given feature along with their statistics we calculated. So besides the dataset location, the dataset ID, and feature IDs, there are a couple other configuration we ask the user to provide us. First is the temporary client credentials. This is what, as Nori mentioned, that we don't want to have a universal credential to have access to all our data sets. So we take this temporary credential from our client to read their feature data set for our stats computation job. And it's like more secure that way so that we don't, so we have like better design pattern. So as we are designing the whole process, we realized there are various aspects of time for a given data set. For example, I have this data set on the right-hand side. Let's say if we want to track someone's biking exercise, we want to track like how far he has gone and like what is the elevation gain for a biking trip. So there's the concept of event time, meaning that when was that biking trip occurred? And then there's also the concept of ETL time, meaning that when does that data set landed in our system? So as a data engineer, maybe I'm more curious of feature statistics based on the ETL time, just to see if my ETL process is running correctly, or if there's any major change of the process. But however, as a data scientist, maybe I'm more interested in the statistics that's aggregated based on event time. For example, if I want to run some analysis for a given user and see like, oh, what's the average biking length for that user for the past 7 or 3 months? So because of that, we provide this additional field called aggregation fields. It lets the user configure what field they want to use to produce these statistics. In that way, our pipeline is a lot more flexible of the statistics we're generating. So now I'm going to talk a little bit more about our stats calculation. So our stats calculation process is running on EMR. And as Nori mentioned that right now we compute some descriptive statistics like mean, max, average, and some quantiles and counts. We also compute PSI, the population stability index, just to kind of measure the distribution between the two data sets. The default behavior of our pipeline right now is to compare the latest partition of a data set versus the partition before. So all our processes are running on EMR, and every individual request it has its own EMR. In that way, so there's like no processes interfering with each other. And also all the results are sent to our enterprise Kafka and saved to our Postgres database as well as S3. One thing I want to mention that we also have a unique job ID associated with every individual stats calculation. It's easier to, in that way, it's easier for us to keep track of the calculation process, like how far the process has run. And also it's easier for us to debug and see like if a stats job has completed or not. So next I'm going to talk a little bit about our Postgres table design. So we have two tables to keep track of our statistic computation. First is to store the stats themselves, and the other is to track the job status. So for the feature stats table, we store every statistic as its own entry, meaning that mean and max, there's their separate entry in this table. The reason we designed that is so that we can have a more flexible table schema. And if we want to add a new statistic into our system, we don't have to change the database schema again and again. We also utilize this parent-child table design. So in the parent table, we only store the index of the child table, and then the request is actually directed to the child table, and all the data are saved in the child table. We partition these tables based on the feature name, just so that it's easier and faster when users try to retrieve their feature statistics. And in our job status table, it tracks of like where the process has run. So the trigger API, the PySpark job, as well as our ingest engine, all connect to this table and update these table in real time. And one other thing I want to mention is we have a Kubernetes cluster managed by a different team. It's very easy to use. They manage those Kubernetes clusters in AWS, and they provide every team and every project their own team namespace and also a personal namespace. As a developer, we can just focus on how to develop our application, and then we can deploy them into like dev, QA, and prod environment. And we, as like our design, our trigger API, ingest engine, and the GraphQL API all running on this Kubernetes cluster. In this way, it's easier to manage them, and everything is auto-scaled up and down based on the request. And then every application is running independently, so they won't interfere with each other. And one last thing I want to talk about is our serving layer. This is like where the fun is. We provide the two major way for user to see their statistics. One is a dashboard and the other is a GraphQL API. So I want to first talk about this dashboard on the left-hand side. We have a very specific use case. Our client has their data set partitioned by ETL time. And within each partition, they keep a whole history of their feature data, meaning that if they have 13 years of data, they keep that in every single partition. This is like very specific for their use case. When they're trying to calculate statistics, what they're interested is they want to see the stats over the time of like when the event actually happened. But they are also curious, like, what if there's any major changes between two partitions? Like how can they see them like faster? So because of that, we provide this panel for them. They can see, as you can see, like the stats themselves are plotted based on the event time. And we provide them the two panels that they can compare side by side for the partition they choose. So the top panel is from the June partition and the bottom is from the May partition. So this is like a very like centralized way for them to have a quick view of their statistics as well as their feature. The second interface we provide is the GraphQL API. It's a more flexible way for user to retrieve their feature stats as however they want. For example, if you want to see an average for a given feature for the past 3 months, you can just query our API, get that data back, and then you can put that in the Jupyter notebook and then just plot them in however way you want, or even do analysis on top of that. As we mentioned earlier, that we partner with the external team, they also use these statistics we generate to run feature drift detection algorithm on top of that. So as a conclusion, these are our 5 key design decisions together with the solution we provided. First is the feature must be accessible, identifiable, and readable. So we have this standard time series ingestion pipeline with the Parquet output, as well as the standard data set and the feature registry that people can uniquely identify data set and the feature. And the second is we want to provide the maximum security ability so that we don't have a universal access to all the data set. We take the client's temporary credential to access their feature only. And the third is the aggregation attributes are configurable. As we said that sometimes people want to see their feature stats aggregated based on different time aspects or even like more other fields. So we let them configure based on their own use, and it's easier for them to get the analysis and statistics on top of those visualization. And also all our process are running in a distributed way. Our PySpark is run on separated EMR cluster, as well as our applications are running on the managed Kubernetes cluster. And lastly, we want to empower users to derive their own conclusions and decisions. So we provide this centralized quick view of a dashboard of the stats that generated, but they can also just get the statistics from us through our API and then run the analysis that fits their use. So this is a wrap for our talk. Thank you so much for listening. Looking forward to meet you guys at our live Q&A session.